Lesson 13.2, Angles and their measure. The definition of trigonometry is the measurement of triangles, including sides and angles. Our focus for the rest of this chapter will be angle location. We're going to take a look at creating angles in any one of the four quadrants on a graph by rotating them. An angle in standard position has to have two things. It has to have an initial ray and a terminal ray. The initial ray, where we start, has the vertex at the center. And then just out to that right-hand side on the x-axis, this would be the initial ray where we would create our angle measure. Now as we rotate, we can rotate up or down depending on what type of measure we're looking for. I'll just rotate this one up a little bit, up into quadrant 1 here. And where my ray or my measure of my angle ends, that's known as my terminal ray. Terminal is where the angle measure ends. So we would put that theta symbol right in between. And that's measuring from standard position. We can have measuring in degrees of all different types. Over on the right-hand side, where that initial ray is located, that would have a measure of 0 degrees. But we could go all the way up to the top and have it be as big as 90 degrees in that quadrant. If we went all the way with that terminal ray to the left-hand side, that would be a 180-degree angle or a straight angle from geometry. Your angle could rotate all the way down to the bottom, and that would be a total of 270 degrees. You could also have your angle rotate all the way around to match the initial ray, and that would be a 300, I'm going to get that 3 to show up there. Sorry about that. That would be a 360-degree rotation. Technically, there are two ways that your angle can rotate, and it depends on the type of measure you're given. If you have a positive angle measure, that means your terminal ray is going to go in a counterclockwise direction. Counterclockwise just means backwards around a clock. And that would be maybe a measure like this. So counting backwards through quadrant 1 into quadrant 2. That would be an example of a positive angle measure. Now if you start at that same term or initial ray and you go in another direction like this, that means your angle is negative. My arrow right there. And you're counting in a clockwise direction. The direction your angle rotates matters because your angle will end up being in a different quadrant otherwise. So we have to watch the type of rotation. Let's try a couple. Sketch each angle. Our first angle is positive 145 degrees. This means we're going to rotate counterclockwise around the coordinate system. And I'll show you what that looks like. We always start with our vertex at the center, and we draw our initial ray to the right-hand side on the x-axis. That's our 0-degree rotation. If I get the boundaries of each of the quadrants, I know at the top, that's already 90 degrees. It would form a right angle. Over on the left-hand side is 180. At the bottom is 270. And if we were to go all the way around, that would bring us back to 360 degrees. Our angle measure, though, is only 145. If I draw the direction with an arc, I'll go up into quadrant 1, over into quadrant 2, just a little bit beyond halfway. So maybe something like that. Using my arrow to show direction, and then labeling my theta. That would be a sketch of a 145-degree angle. Let's go ahead and try another one, negative 265. Because this is a negative angle measure, we're going to rotate clockwise. The consistency with these rotations is we always start with our vertex at the center and our initial ray on the right-hand side. There's 0 degrees. But if I count clockwise, watch what happens to my boundaries. At the bottom of the graph, instead of 270, that's actually going to be negative 90 degrees because I'm going in that unique new direction. On the left-hand side, it's even negative, but it's 180, the same as it was for our first graph. And then up at the top, we just kind of flip-flop the top and the bottom. If we rotated clockwise all the way up to the top, that would be negative 270. And if we went clockwise all the way around, that would be negative 360 degrees. So let's think about where we'd stop at 265 in that clockwise direction. I'm just going to draw my arc through quadrant 4 down to negative 90. On the left-hand side, negative 180, Notice 265 is super, super close to 270. So I'm just going to draw my arc or my terminal ray up there, use my arrow to show direction, and that's just an example of a clockwise direction or a negative angle rotation. Our goal is to get a close approximate of the quadrant it's supposed to be in. We're not looking for an exact location. That would be too tedious with the space that we have. Sometimes angles will rotate more than one loop around the circle or around the coordinate system and still match with a terminal ray. These are called coterminal angles. We're going to look at them today in degree form. So they're angles that share the same initial and terminal rays, but they're not the same number. Terminal, there we go. Is that spelled correctly? Yes, terminal rays. Typically, you'll always have one positive coterminal measure, and you'll include one negative coterminal measure. So you'll have one of each. That way you can go counterclockwise or clockwise. The formula is super simple. Start with your given angle, so we'll label that as theta, and then you literally just add and subtract what it would take to get one full loop around from where you're at, which is 360 degrees. Let's look at a couple of examples down below. Determine what quadrant each angle is in. Then find one positive and one negative coterminal angle. All right, we'll start with 58 degrees. That's going to be a counterclockwise rotation. I'm going to start with my vertex at the center and my initial ray on the right. If I start at 0 degrees, I know that up at the top is 90. 58 degrees isn't even further than that, so that's the only one I'm going to label. If I rotate counterclockwise up into quadrant 1, it's a little bit more than halfway. So I'll maybe go to that location on my graph. There's my theta, 58 degrees. To do coterminal, we literally just take our theta and we add and subtract 360. So if I take 58 and I add 360 to it, we get an angle that's bigger than 360. It's 418 degrees. If we graphed that, we would just go all the way around our coordinate system once, and we'd still stop where that terminal ray is in quadrant 1. If we go in the clockwise direction, meaning we subtract 360, we would get negative 302 degrees. We'd start with our initial ray and then still rotate clockwise 302 degrees, and we end up on that terminal side. And that's finding coterminal angles. What happens if our angle's already bigger than 360 degrees? Well, we figure out what's left over. I'll start with my initial side of 0. Now I know that I have 90, I have 180, 270, and 360. But I need to keep going because it's 500. So if I go back up to the top after 360, that would be 450 degrees. And if I even go further to that left-hand side, that would be 540 degrees. So I know I won't have to go more than 1.5 times around, so let's approximate where we'll be. Starting on that initial side, I'm going to go up and around one full loop. That's already 360. To the top is 450. So if I have to go between 450 and 540, we're going to be slightly beyond halfway. So I'm just going to approximate it, I don't know, about right there. That looks a little too far. So maybe I'll stop it a little sooner than that. Maybe like right there. We'll go there. And that crazy big loop is our theta, 500 degrees. To make that now coterminal, remember we just add and subtract 360. So if I do 500 plus 360, I get an even bigger answer. That's going to be 860 degrees. But we have to be careful on this one, and I put this one on here specifically for the second part. If we do 500 minus 360, normally we would get a negative rotation, but this becomes positive 140. So that means it's still positive. It doesn't count as a negative measure. So guess what? We have to add or subtract 360 again. I'm going to take that 140 degrees. If I subtract 360 one more time, then I get an answer that's going to be valid. Our 140 minus 360 is negative 220 degrees. So either one of these top two angles would be fair game for your positive rotation, but you had to subtract 360 twice to get that negative rotation. Here's another scenario that you might see. What if your angle starts off negative? That just means we go clockwise. So we kind of have to figure out our boundaries accordingly. Vertex at the center, 0 on the right-hand side. If we're going clockwise, we have -90 and then -180. So I can stop right there because I know we're not going to go further than that location. If I'm going clockwise, I'm going to arc down through -90. 134 is almost to the halfway point. So I'm just going to try to go right in the center with my arrow to indicate direction. -134 degrees. Now, to get coterminal, we still apply the same rule. -134. If we add 360 to it, we get positive 226 degrees. That would start and end at the same location, but rotate counterclockwise. If we take -134 and subtract 360, we get -494 degrees. So that would be another clockwise rotation that would go all the way around and stop at that terminal ray. And here's where things will definitely start to get more challenging. Another way to kind of find rotation around the quadrants is by finding what's known as radian measure. So a radian measure is found when we place a circle with a center right at the middle or the origin of a coordinate system. So a radian is the measure of a central angle that intercepts an arc on a circle. The unique thing about radian measure is it's not a degree answer. It's going to be length on the circle. So if we think about length around a circle, that brings us to circumference, something you talked about in geometry. The formula for circumference of a circle is 2 times pi times r, and r would be your radius. If we consider the radius of this circle, just make it a template or like a default it to 1, then the circumference of this circle is just 2 pi units, whatever you would be measuring in. So let's go take a look at this picture in a little more detail. You'll notice when you intercept an arc that you always have your initial ray and you'll have a terminal ray, just like we did before. But that angle in the middle, theta, is your degree angle, and we're looking for length. So the radian measure is this green right here, is that letter S. That's the length on the circle that matches the degree rotation. So that's known as the radian measure. If we think about kind of dividing up the quadrants just like we did with degrees, one thing that will always be consistent is we'll always start with 0 on that right-hand side. Now the divisions are going to be based on the fact that going all the way around, if we went all the way around, that would be 2 pi radians. But we want to divvy up the in-between stuff so that we can determine where to sketch our graphs. So if I think about cutting 2 pi in half, halfway around this circle would have a distance on the circle of 1 pi. And we often just refer to that as pi. Very rarely will we put the 1 out in front. At the top, if you're halfway between 0 pi and 1 pi, that's 1/2 pi or pi over 2. At the bottom, between 1 pi and 2 pi, halfway in the middle would be 1/2 or 3 pi over 2. Get to know those locations in radian form. We're going to use those throughout the rest of the chapter. To help us transition from one form to the other, we have some pretty straightforward formulas. If the distance around a circle is 360 degrees around the coordinate system, and the distance on the circle is 2 pi, then to go from degrees to radians, you would multiply by 2 pi divided by 360, or pi over 180 if you reduce that. So I'm going to write that out again for you. If you have a degree and you want to convert it to radians, technically you would multiply it by 2 pi over 360, because that's the conversion from one loop around the circle to one loop in degrees around the origin. But we can reduce this to make it even easier to simplify. 2 over 360 reduces to 1 pi over 180. So take your degree measure, that theta symbol, multiply it by pi, and then divide by 180. Your answer will have pi in it, and you always want to reduce the fraction. Your answer will be a radian measure when you're done. So let's try the 2 down below. Convert from degrees to radians. We know we have degrees because we've got little degree symbols right here that lets us know the form we're in. Now a 20-degree rotation would start on the right-hand side and rotate counterclockwise very slightly into quadrant 1. Therefore, our radian measure, our length on the circle, would be pretty small as well. If we take 20 times pi over 180, I'm just going to put 20 over 1 and multiply straight across, which just gives us a big fraction to simplify. 20 divided by 180, I could just cross off the zeros. That would be dividing them both by 10. 2 goes into 18 9 times. Therefore, this fraction reduces to pi over 9. That would be the radian length, that part of the circumference, that equals that 20-degree rotation. If your angle's negative, it just means your radian will also be negative. So it's really not that much different to work with. Again, if it's a degree form, we'll multiply by pi and then divide by 180. I'm literally just going to put negative 250 over 1 again, and then multiply straight across. Negative 250 pi over 180. Notice they both end in 0, so we can divide by 10 on top and bottom. After that, though, the negative 25 and the 18 do not simplify any further. So our radian measure in a clockwise direction would be negative 25 pi over 18, that portion of the total circumference. And the last thing we'll do in the video today is to go backwards. We'll just start with a radian measure and we'll convert it 2 degrees. When we go backwards, we take our radian measure, and we still call it theta, but it's a radian this time. And instead of multiplying by pi over 180, we multiply by the reciprocal. So we're just going to multiply by 180 over pi. And then from there, reduce or simplify if possible. So if we have 3 pi over 4 down below, and we want to convert that to degree mode, I'm just going to multiply by 180 over pi. The nice thing about a problem like this is there's a pi in the numerator and denominator, and they cross off. Now, 3 times 180 is 540, but if you divide 540 by 4, you get 135. And because you want a degree answer, make sure you label it with a degree symbol. Now, if there isn't a pi in your original radian, if they've approximated it, that means we have to plug in pi on our calculator. We have a negative radian, which means we're going to have a negative degree as well. If we take negative 3.14159 times 180, but divide by pi, go ahead and plug that into your calculator. You should get negative 180 degrees. 3.14159 is a decimal approximation for pi, so ultimately it would cancel out. And that's where we'll stop for the first part of the 13.2 video.